Welcome to the second video in our quantum mechanics series, where we will dive deep into one of the most fascinating and mind-bending fields of physics. We will cover not only the conceptual side of quantum mechanics, but also the mathematical foundations that are essential to truly understand the subject. Step by step, you will gain insight into both the theories and the equations that govern quantum phenomena. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the second lecture on quantum mechanics. Now, when we study quantum mechanics, we see that photons are fundamental particles of light and electromagnetic radiation, demonstrating wave-particle duality, which is very central to understanding quantum phenomena. They exhibit quantized energy and momentum, interact with matter at discrete levels, and hence we will start today's lesson, or I would say video, first with understanding some of the basic properties and what lead to photons. Now, as you can see right on the screen, that photons are basically particles, I would say particle-like quanta of electromagnetic radiation. Now, if I go by the method, then we use the standard c as the speed of light, momentum as p, and here I am using epsilon instead of energy of E as energy. Now, from here, what we can see that there are two equations that emerge. First one is this, P equals to h upon lambda. Now, what is this equation and why it is important, I will tell you. First, let us understand the elements. This is the Planck's constant, and if you have not watched my first video in this series of lectures, then you should watch the first video which I have given in the I button. What is Planck's constant, why it is so fundamental, all these things I have discussed in the first video. Lambda, this is the wavelength of the photon, and P as usual is the momentum of the photon. So for, all in all, from this particular equation, what we can say is that this equation shows that the momentum of a photon is inversely proportional to its wavelength. The second equation which emerges is this, epsilon equals to hc upon lambda, where obviously epsilon denotes the energy of the photon, c is the speed of light, h I am not mentioning is the Planck's constant, and lambda as usual is the wavelength. Now, this equation also tells us that the photon's energy is also inversely proportional to its wavelength. Now, these two equations are fundamental in quantum mechanics and physics because they describe properties of photons like momentum and energy, link the wave-like and particle-like behaviors and other forms of electromagnetic radiation that are particularly important. Now, these are equation methods, mathematics, we understand that. But what is also important for us to know that how these equations can be used to some extent in our practical life. So as you can see that the inverse relationships with wavelength lambda highlights why I would say higher frequency, that means shorter wavelengths, electromagnetic waves like X-rays or gamma rays carry more energy and momentum than lower frequency waves like visible light or radio waves. So from this particular, I would say, equation, what we can find, first of all, is this one. It shows that light's energy depends on its wavelength. Also, what it highlights is that the concept of quantized energy, where the word quantum emerged, showing that each photon carries a discrete packet of energy which is proportional to its frequency. That means it is defying the usual classical notion that energy will be continuous and it will go on and go on. These things we have seen in the first video, how it leads to what is called the ultraviolet catastrophe. It also is important because it is very fundamental to our understanding of how atoms interact with light. And what do we mean by that? We will look in today's video. And it is particularly important in absorption and emission process. Lastly, the energy of incoming photons also are important in generating solar cells. That means it must match into materials band gap to effectively generate electric current. The next thing which comes up is also this one. This is the energy. This one is P equals to h upon lambda. This shows that light can exert force just like macro particles in classical physics. They also have photons have momentum even though its mass is less, and this is very crucial in explaining phenomena like photoelectric effect. Second is that it explains radiation pressure, the force exerted by light when it strikes or it absorbs on a particular surface. We will look into what we mean by that. Now, for the time being, what we can do is that let us take an, this kind of a photon, which is nice and it shows a nice animation. So, for example, this photon, there is a momentum and energy of the photon, but remember they are very, very tiny. It is very, very small. Now, if I take the, the wavelength as 663 nanometer or something like that, then we get a kind of a, momentum which is 10 to the power minus 27 Js and energy which is equal to that. So as you can see from these figures, it is very clear that these things are very small, minuscule, very tiny on microscopic on the scale. And what we also note is that an electron volt or 1 eV is equals to this much, and it is a useful unit for the energy of a photon. So visible photons, we can say that have energies of the order of an eV, which is an electron volt, and X-ray photons, I have tried to mention this in the illustration, also have energies which are in the order of 10 kilo electron volt. So this is basically to give you an understanding that how small they are and how these equations actually help us in understanding the quantized nature, the photoelectric effect, and creating of solar cells and other manufacturing equipments which are very important in our daily life. So from here automatically the question emerges that, as we saw, that why do we study at all photons in quantum mechanics? Why don't we start with X-ray or gamma rays, etc.? So in this part of the video I'm going to give you a very clear explanation on why do we study photons in quantum mechanics. Now, the first thing, the reason is definitely what is called the photoelectric effect. We will deal with that later, but photoelectric effect is the phenomena explained by Einstein, which demonstrates the particle-like nature of light. And this is the photoelectric effect, and later the Brownian motion, for which he received the Nobel Prize in physics. The second thing which is very important is called quantum entanglement. So we know that photons can become entangled. So a photon on Earth can exactly know what is happening to other photon at Alpha Centauri or a far away distance. It means that their properties are correlated to each other, even when they're separated by large distances. The third thing is that fundamental force. That means what? That means that photons are the building blocks of light and essential for understanding of the fundamental principles of quantum mechanics. Their unique properties have led to numerous technological advancements, which continues to be of a very interesting subject of research. Also, quantum computing. Photons are used in quantum computing as qubits, the basics of units of information. And another part which I have not mentioned is quantum cryptography, where photons can be used to transmit information securely using quantum distribution. So all in all, what we can say is that photons are definitely the building blocks of light and are essential for the understanding of the fundamental principles of quantum mechanics, and their unique properties are giving numerous technological advancements. And also in the area of quantum electrodynamics, photons are the force carriers of the electromagnetic force, which leads to a lot of discoveries and researches which are still going on. Now, once we study the reason that why do we study photons, prior to that we saw what are photons and what are the two equations which leads to this. We come to a very important discovery right at this moment in our video of this lesson, and this discovery led to a very important, I would say, a conclusion, which is a kind of an exit from the typical classical field and going into quantum field, and that is what is called the Compton effect. And we are going to look into what is Compton effect. But prior to that, what we need to understand a little bit about the classical nature of light or classical physics which existed prior to Compton effect, so that then we can understand actually how Compton effect has brought in the results. The first thing, as you can see this animation, which is a kind of a wavy wave. During the early days, light was purely thought of as a wave, and it has got no particle-like properties, as has been described by Isaac Newton, which is called the corpuscular theory of light. Also, the second part is that I imagine this blue circle which is going on and on and on. So energy transfer is continuous. And remember that dependent on the wave intensity, not on frequency or quantized packets. I mean to say this is prior to the Arthur Compton's discovery. Also, these bouncing lines, remember that light waves have no particle, I would say no particle-like momentum and cannot transfer momentum to other particles in a collision. So it didn't have any particle-like momentum. The third thing is that when we use scattering of the incident ray and the scattered ray, early days the classical physics tells that scattering does not change the wavelength of a light. Indeed, wavelength should remain the same independent of the angle. Again, I repeat, the wavelength should remain the same independent of the angle. This is what we are talking of the classical era. Also, you will see that light waves interact smoothly with electrons without discrete energy shifts. That means it will go on and interact smoothly and smoothly and smoothly, and there are no discrete kind of energy shifts. Now, this was basically the era or the time of physics when we are talking prior to Arthur Compton's discovery. Now we will look into the Compton effect and why this discovery ushered a new era in the modern physics. Now this is Arthur Holly Compton, and what he discovered is known as Compton effect, also called as Compton scattering. We will come to this. There's this clear line of distinction or relationship between Compton effect and Compton scattering. So what did he discover is this. So he discovered where X-rays scatter off free electrons, resulting in an increase in their wavelength and a decrease in their energy. And this effect provides a strong evidence for the particle-like nature of light, which supported later Einstein's discovery on the photoelectric effect. Now, just few seconds back, if you go back to the video, I have told that during the scattering effect, there was no change in the wavelength, or the angle would remain the same. Here what Professor Compton says is that there is resulting in an increase in their wavelength and a decrease in their energy. How that can happen? Because classical physics tells that it would continue smoothly. So this is a kind of a pictorial description of what is a Compton effect. You see an incident photon, which is mentioned as lambda I. It targets an electron at rest. Then there is a recoil of electron, which is phi, and there is a scattered photon, which has got a wavelength of lambda f and an angle of theta. So the effect which was discovered by Arthur Holly Compton while he was researching in X-ray actually fetched him the Nobel Prize in Physics, and in 1927. Now we understand this, that is an exit from the classical era, ushering a new era in modern physics. But what actually step-by-step Compton effect means, let us look into the next part of the video. I will keep the photo or the illustration on the left hand side so that you can see and then you can visualize better. So step number 1 was called the photon-electron collision. So what happened when we shine a high energy photon like an X-ray or a gamma ray, it collides with a loosely bound or a free electron, and the photon transfers some of its amount of its energy to the electron. So the Compton effect first showed that if we shine a high energy photon, it collides with a loosely bound electron which is supposed to be at rest, and the photon transfers some amount of energy to the electron. Due to this, the step 2 what happens is a scattering, and after the collision the photon is scattered in different directions with longer wavelength, which obviously means lower energy. And step number 3 is that when the scattering happens, obviously there is a change in wavelength, and this is called the wavelength shift, and this shift is known as the Compton shift and depends on the angle at which the photon is scattered. So first we shine an high energy photon, it hits an electron and there is some amount of energy. Once the energy is transferred, obviously there is a scattering of the photon, and this scattering definitely creates a change in the wavelength, and it depends on the angle at which the photon is scattered. Fourthly, what it proves is the particle nature of light. So now you see we are coming out of the corpuscular theory of light. From the wave we are coming to particle. So this phenomena confirms very well that light behaves as particles, both ways. Light behaves like particles and particles behave like waves, and that is why quantum mechanics is called to be weird. With quantized energy, not as classical physics till it is continuous, with quantized discrete energy packets, and it supports Einstein's photon theory, which is called the wave-particle duality. And finally, what it also shows is the energy and momentum. Obviously, it will become conserved because Compton scattering obeys the classical principles of energy and momentum observation, with energy transferred from the photon during the electron during the to the electron during the interaction. So 3 quick summaries which comes up from the Compton effect. Number 1, it confirms the quantized nature of light and supports the wave particle duality. 2, it very much validates the photon model of light, where light consists of discrete energy, that means packets. And third, photons possesses both wave and particle properties. Remember, it possesses both wave and particle properties, something which classical physics could not explain. So we come to these 3 final conclusions explaining what actually Compton effect is and what are the results out of that. But the question still lies in our mind that what is about the scattering? We talked about the scattering of the angle. There is a change. What is that? Let us look into the next part of our video. This is a kind of a diagram where you can see that Pi is the incident photon, and it transfers momentum to a stationary electron, the electron as you can see on the screen, so that the scattered photon has a lower momentum and hence a longer wavelength. Now here I would like to highlight few points. This one is the incident photon, and here you can see that when the photon is scattered through an angle theta, this photon hits it and it is scattered by angle theta by a stationary electron of mass me, then it is given, the increased wavelength is given by this. Now hold on, I'm going to explain this part by part. The reason is that this is very central in our understanding of quantum physics. Now first we will go by what do you mean by this delta lambda. Now this is the change in the photon's wavelength due to the scattering. Now there are 2 things which you have to keep it in mind. One thing is that the photon and its behavior before the scattering, another is hitting the electron and after the scattering. The next one is the Planck's constant, a fundamental constant in quantum mechanics, which I have already explained. Me is basically the electron's rest mass. It is the electron's mass. It comes to now round about 9.10 times 10 to the power minus 31 kilogram. And c obviously is the universal constant, the speed of light, and this theta is the scattering, which is the angle between the direction of the incoming and the scattered photon. So we will look more into that, don't worry. But first of all, let us understand what this equation conveys. It tells us that how much the wavelength of the photon changes after colliding with an electron based on the angle of scattering. Earlier physics told that there is no change in the scattering. It goes on continuously, but here on the Compton effect we say that there is a change in the angle, of the photon changes due to the angle of scattering. Now in the next part of the video, let us now look into the equation a little bit more in a detailed manner so that we can understand that. So we take the same equation, isn't it? We take the left hand side, that is the delta lambda. So the left hand side of the equation, delta lambda, represents the change in wavelength of the photon after it hits the electron. When it hits, as I showed you, there is some amount of energy being transferred to the electron. So what is the change in the wavelength? So mathematically we can say this one, delta lambda equal to lambda phi minus lambda, where lambda phi is the wavelength of the photon after scattering, obviously, and lambda is the initial wavelength of the incoming photon before scattering. So after minus before gives you the delta lambda. Now step 2 is that we need to understand h upon me by c. Now the term h upon me by c is known as the Compton wavelength of the electron. It is a constant value that characterizes the electron's response to photon interaction. And this is the value, h upon me by c, roughly about 2.432 times 10 to the power 12 m. So this value actually represents the maximum possible, I would say, wavelength shift that can occur for an X-ray or gamma ray photon scattering of an electron at rest. So it actually depends on fundamental constant, and it is a measure of what we can say is the quantum mechanical size of the electron in the context of scattering events. Now we come to the step 3, the final factor 1 minus cos theta. This is something which relates to the angle of the scattering angle, which is the theta, which is the angle between the initial direction of the photon and the direction of the scattering. So suppose theta equals to 0 degree, that means no scattering, photon continues in a straight line, cos theta equals to 1. So 1 minus cos theta equals to 0. So it means that there is no scattering and delta lambda equals to 0. The second thing is that suppose theta equals to 180 degrees and cos theta equals to minus 1. So 1 minus cos theta will be equal to 2, which means that it gives the maximum wavelength shift of this. So what it shows actually is that this factor shows that the larger the scattering angle, the greater the change in wavelength. So the larger the scattering angle, the greater the change of the wavelength in photon. So the wavelength shift is 0 if photon is scattered in the original direction, and maximum when it is scattered directly back. So this is how actually the equation looks like. So from here what we can summarize is that it expresses how much the wavelength of a photon changes after colliding with an electron based on its scattering effect. It reflects two things. One is that quantum mechanical behavior. That means it shows that they transfer discrete momentum and energy, not continuous as thought by classical physics, and depends upon the scattering angle. That means the photon's wavelength shift increases as the scattering angle increases, reaching a maximum for a direction backward scattering. So this is how we decipher one by one the components of the equation. Now we will come to a very, very simple yet a very profound understanding that how we can derive this equation. I mean to say the derivation part. And for that what I am going to do, I am going to take two figures. This is the incident photon, which has got an energy each equals to h nu, and this is before the collision. This is after the collision. There is a recoil electron and there is a scattered photon, which is E prime equals to h nu prime. Now we need to remember one thing very clearly. We have to remember one thing very clearly, that Compton succeeded. So here it is. Okay, first let me tell you this part. E equals to h nu, consider that the incident photon of energy equals to h nu, and there is a momentum, which is this is the scattered photon's energy, and this is the, I would say, if the photon scatters with a momentum p, which is before this, then it scatters at momentum p prime at an angle theta, while the electron recoils with a momentum PE. Now here you can see there is a PE, which is the on the top on the right hand side. This is a PE, which is the electron which recoils with a momentum, and it conserves actually the linear momentum. So what is important is that Compton succeeded in explaining his experimental results only after treating the incident radiation as a stream of particles, photons, colliding elastically with individual particles. So just like kind of a billiard ball analogy, you can think that the incident radiation is bringing a stream of billiard balls and they are colliding with another billiard balls, which are electrons. So from here what we can say is that when it creates an angle theta, which you can see here, and the electron recoils with a momentum PE, then the conservation of the momentum yields energy equals to E equals to h nu, and momentum equals to P h nu upon C. So from here we go back to this same figure, and here you can see, now I have highlighted. I'm so sorry, it should have been highlighted earlier, but anyway, so this is the recoiling electron, it is the scattered electron, and from here what we can get is this one. Squaring both the sides, we get this kind of a value. Now after this, I have omitted few steps to make things easy. If we substitute the momentum of photons and electrons in terms of frequency and energy, what we get is this. You can do the calculation later. This is just a plus b whole square, simple algebra. Then I have substituted values, it goes into this, and once we rearrange and refactor, we get into this kind of an equation. Further, what I do is that I will divide both sides by c squared, and I will get something like this. Now we know that initial energy equals to energy of the incident photon plus the rest energy of the electron, which will be equals to this. Final energy will be energy of the scattered photon plus total energy of the recoiling electron, which is h nu plus EE. And the total energy of the particle E as related to momentum and the rest mass is something like this. So for the recoiling electron, we have something like this. Now the total momentum from there we can, so from here you can see which we started, we finally got into this. Now what we see from here is that the total momentum before the collision is equals to what? H nu upon C. The final momentum, if you can go back to this slide, here you can see initial and final energy. Now we are dealing with the total momentum and this, and the final momentum equals to momentum of the scattered photon plus momentum of the recoiling electron. If you go back, you will see the same pattern over here. Energy of the scattered photon plus total energy of the recoiling electron. Here also you see that the momentum of the scattered photon plus momentum of the recoiling electron is given by this. Now if I substitute momentum energy equation and simplify, we get an equation something like this. And we know that energy of the incident and the scattered photon are given by this. So the conservation law follows, which is this one. And from here it goes a little bit long. I mean to say this is how the equation looks like. So this equation can be further taken and given into this form, which can be further deduced by squaring both the sides. We get this, and finally we get this one. So I will take the last equation. I would like to show you what actually is important. So here you can see this lambda C, this is actually this. So earlier I have made it around 2.42. So this is approximately same. So this is how we get the Compton wavelength of the electron. You can go back to the derivation of the equation one by one. I have tried to follow a similar format. So from here what we can see that the wavelength shift of the X-rays depends only on the angle at which they are scattered and not on the frequency or wavelength of the incident photons. So the Compton effect or the Compton's discovery proved us this. It confirmed that photons behave like particles and they collide with electrons like material particles. Now, I have been talking about what is called a Compton effect and what is called a Compton scattering. Now, this actually has got, is it the same? Is it something distinct? Is it something which has got a difference? Let us look into the next part of the video. What is Compton effect and what is Compton scattering? Now, if I go by first with the definition part, then you see this is describe the phenomena where X-ray and gamma ray photons increase in wavelength when electrons are scattered. And this refers specifically to the process of photon colliding with a stationary electron and scattering at an angle. If I go by the nature, then there is a shift in wavelength due to the photon-electron interaction, and here the photon's direction changes, transferring energy and momentum to the electron. It provides some energy to the electron. The key discovery is that Compton effect shows established photons particle-like properties showing quantized energy and momentum energy. Compton scattering shows how photons interact with electrons in particle-like collisions consistent with quantum mechanical laws. So this is how things happen. You can say this is a kind of a relationship. Further, if we see by the mathematical description, the significance, then this is a key evidence of wave-particle duality in quantum physics, which leads to the acceptance of the photons as quantized particles. Also, if you see in Compton scattering, these are observed in experiments validating the quantum mechanical behavior of photons and electrons in scattering events. Classical versus quantum, the Compton effect contradicts classical wave theory supporting quantum mechanics through particle-like behavior, and Compton scattering shows discrete interactions between photons and electrons unlike classical waves. So in summary, what we can say is that the Compton effect is the broader phenomena. The Compton scattering is a specific interaction process that demonstrates this effect, and both terms highlight photon-electron interactions and are foundation. They are the foundation of the current understanding of our quantum physics. So that's all. We will take a pause in today's lesson. Lesson number 2, we are done, and we will continue with that. Thank you very much for those who have watched it and taken up your valuable time. Please do subscribe to my channel by clicking on the bell icon and click on all to get all the notification from Physics for Students. You can contact me at this ID, and I've already started putting up fresh, new and interesting videos starting in this new channel, General Relativity Explained, where I'm teaching again general theory of relativity in a different way, step by step on this channel. You can subscribe to that channel, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will continue its journey on all the different subjects and courses that have launched in modern physics, general relativity and so on. And I will keep you providing quality information and videos on quantum mechanics, physics on both this channel and the other channel. See you soon in the next video. But till then, may the good Lord be with you.